Hi, we are back on our discussion, this time about nuclear chemistry. In this topic, we'll discuss balancing nuclear reaction. In our previous discussion, we compare chemical reaction with nuclear reaction. The comparison, we discussed that a chemical reaction occur when bonds are broken, whereas nuclear reaction occur when nuclei emits particle or rays. Likewise, in a chemical reaction, atoms remain unchanged although they may be rearranged. In the case of nuclear reaction, atoms are converted into atoms of another elements. Therefore, balancing nuclear reaction is totally different like what you have done in your general chemistry when balancing chemical reaction. In a chemical reaction, you observe the law of conservation of mass by balancing the number of atoms of each element in the reactant must be equal to the atoms of the element present in the product. In balancing nuclear reaction, the nuclear reaction is balanced when the total number of protons plus the number of neutrons in the product and in the reactants are the same, and this is the conservation of the mass number. The total number of the nuclear charges in the product and in the reactant are also the same. And this is observing the conservation of atomic number. This can be done by considering the following elemental particles as either reactant or product. These elemental particles are proton, symbol P, or the symbol for hydrogen, with atomic number of 1 and a mass of 1. And the mass is approximately 1 atomic mass unit and a charge of positive 1. Whereas neutron with a charge of 0 and a mass of 1. And electron or beta particle with a charge of negative 1 and a mass of 0. Or a positron, which is symbolized as positive electron or a positive beta with a mass of 0 and a charge of positive 1. Or an alpha particle, which can be represented by an helium atom with a charge of positive 2 and a mass of 4. Or the alpha symbol with a charge of positive 2 and a mass of atomic mass unit. Or a gamma, which has a charge of 0 and a mass of 0. Okay, let us apply this technique of balancing nuclear reaction. A nuclear reaction is balanced when the total number of proton plus the neutron in the product and the reactant are the same. That is a way of conserving the mass number. Or the conservation of atomic number is applied when the total number of nuclear charge in the product and in the reactant are the same. Let us have some example to illustrate the technique in balancing nuclear reaction. Okay, to illustrate the technique in balancing nuclear reaction, we are asked to balance the following nuclear reaction. For the first number, we are given here polonium-212 with the atomic number of 84. This is your reactant and your product is lead-208 plus a blank. So, we have here the atomic number, which is denoted by the charge, which is the number of proton, must be equal. The reactant and the product must be equal. So we have here 84, we have 82, so we must have 2 here, and 212 minus 208, that would give you 4. So we have a particle with a mass of 4 and a charge of 2, that is your helium. Okay, or an alpha particle with an atomic number of 2 and a mass of 4, or a charge of positive 2 and a mass of 4. Okay, so that's how you balance a nuclear reaction. The mass number of the reactant and the total mass number in the product must be equal. Likewise, for the atomic number, which is the charge, referring to the charge, the number of proton in the nucleus. Okay, we have 84 in the reactant, we have 82 plus 2, that gives you 84. Okay, we have balanced reaction. Okay, next we have here cesium 55, and we have barium here 56, and the mass number is 137. So 137, so it has a mass of 0. The particle here must have a mass of 0. And you have 55, 56, so this must be equal to that. We have deduct 1. 56 minus 1 is 55. So we are referring to your beta particle. Or you can rewrite it as negative 1, 0. So that is an electron or a beta particle is missing in the product side. Okay, moving on. Okay, for the third number, we have arsenic 78 with a atomic number 34 or a charge of positive 33. Okay, for the third number, we have arsenic 78 and the atomic number 33, which is the charge positive 33, referring to the number of proton. On the product side, we have a beta particle here, negative 1. So we must have atomic number 34 because 34 minus 1 is 33 to balance that. Since it is a mass of 0, we have 78 also. 78 plus 0 is 78. So using your periodic table, you look for an element whose atomic number is 34, and that is selenium 78. Okay. Okay, now. So this is an electron capture. Okay, argon 37 captured a beta particle or an electron. So 18 minus 1, we have 17 on the product side. And 37 plus 0, so the mass number is 37 as well. Okay, so you see again your periodic table. We look for the element whose atomic number is 17, and that is your chlorine. Okay, 37. Okay, now next we have here uranium that decomposes to lead 206 and a blank number of alpha particle and an unknown number of beta particle. Okay, so again, the charges must be equal. The number of charges in the reactant must be equal to the charges in the product side. Likewise, to conserve the mass number, the mass on the reactant must be equal to the sum of the masses on the product side. Okay, to begin with, we have here 92 for your charge in the reactant. On the product side, we have 82. And we have here an alpha, which has a charge of positive 2 and a beta of negative 1. Okay. So we can have 92 minus 82. That will give you a charge of 10. A difference of 10 here. Okay. If we put this 5 here, it will not balance there because we still have negative 1. So the next thing we have to check is since the mass of beta is 0, so the total mass of the reactant, the mass number of the reactant must also referring to the sum of the mass on the product for the lead and the alpha only. Okay, so we have 238 here minus 206. we can have it 238 minus 206. That would give you a difference of 2 32. Okay, so 32 divided by 4 would give you 8. So 8 times 4 is 32, plus 206 would give you 238. Okay, we have balanced the mass. So let us check. If 92 minus 82 is 10, difference of 10. And we have here 8 times 2, that is 16. Okay, so 82 plus 16 would give you 8. And 98. But it must be only 92. So if we have 92 here, if we deduct, this must be 6. So this must be 6 beta particle. Okay, again to check, 82 plus 16 minus 6. And that gives you 92. 16 minus 6 is 10, so that is the difference there. Okay, here we can have 10. If we multiply this by 5, it's different. So we have to check first the mass number, because beta particle has 0 mass. So it's easier for us to balance it in terms of the mass number of the lead and the unknown number of alpha particle. Okay. Okay. For part B, we are asked to complete the following nuclear reaction by identifying the X. Okay, in this case, we have here cobalt 59 in the reactant side with deuterium. And the product is you have an unknown X and cobalt 60. Okay, so 59 plus 2 will give you 61. And we already have here 60 for the mass number of cobalt 60. So we have a missing 1 in the mass number for X. So we have here 27 plus 1 is 28. And we have 27 here for cobalt. So this must be also 1. And if you refer to our table for our elementary particle, and we are referring to proton. So your X is equal to a proton, 1, 1, or we can symbolize it using the symbol for hydrogen. Okay. So that would be your value for your X in this equation. Okay. For the next number, we have uranium 235 that is bombarded with a neutron, producing krypton 94 and barium 138 and 3x, which is unknown. Again, the mass number in the reactant side is 235 plus 1, that gives you 236 as the mass number. On the reactant side, we have 94 plus 139. And that gives you 13, carry 1, 233. We have 236. So there must be 3 here. And it is 3 divided by 3 is 1. Okay, so the X would have a mass number 1. For the charges, we have 92 here. And on the product side, we have 36 plus 56. And that gives you 12, carry 1, 92. Therefore, we have 0 here. Okay. And a particle which has a charge of 0 and a mass of 1 is a neutron. So therefore, your X here is a neutron. Okay. Okay, moving on to the third number. We have here chromium, 53. Okay, we have an alpha ray at the reactant side and X on the product side and a neutron. So to total the charges, here we have 24 plus 2, we have a charge of 26. And we have 0 for the neutron, so this has a charge of 26, the X. And likewise, for the mass number, we have 53 plus 4, that gives you 57. Minus 1, so this must be 56. So and the X here is an element which atomic number is 26. Now, referring to your periodic table, element 26 is iron. So X is iron, 26, 56. Okay, that is an isotopes of iron with a mass number of 56. Okay. Now, for the fourth number, we have here potassium 40 emitting a beta particle and an unknown element X. Okay. So since we have here a charge of 19 in the reactant and a beta in the product, so this must, the unknown X must have a charge of 20. 20 minus 1 is 19. And since the mass of the beta is 0, so therefore the mass number of X is also 40. Again, referring to your periodic table, the element whose atomic number is 20 is calcium here. So your X, therefore, for number 4 is calcium. 20 with a mass of 40. Okay. For the fifth number, we have cobalt 59 that is bombarded with a neutron producing an X particle and manganese 56. Okay, to balance the charges, we have 27 here. 27 plus 0 is 27 minus 25, so this must have a charge of 2. For the mass number, we have 59 plus 1, that's 60. 60 minus 56 is 4 to balance that, or 4 plus 56 is 60. So that particle is an alpha particle, okay, with a mass of 4 and a charge of 2. Okay, therefore your X is an alpha particle with a mass of 4 and a charge of 2, or you have the helium atom, a charge of 2 and a mass of 4. Okay, the representation of alpha can be represented by an helium atom. Okay, for the last number, we have uranium 235 bombarded with neutron. And the product is strontium 99 and tellurium 135 plus 2x. Again, to balance the charges, we have 92 plus 0. So we have 92 here. On the product side, we have 40 plus 52, that is 92. Therefore, the charge of X is 0. Okay, now, For the mass number, we have 235 plus 1. That gives you 236. So we have 236 for the mass number on the reactant. On the product side, we have 99 plus 135. So that gives you 14, 3, 2, 234. So we have a missing of 2 mass unit. And you divide that by 2, so we have 1. So X here is a neutron with a charge of 0 and a mass of 1. Okay, that's all for balancing nuclear reaction. We'll have more of this in our future discussion on the different types of nuclear reaction. Then see you then when we discuss more in details of the different types of nuclear reaction.